Okay, so welcome everybody to this first in the revived series of the Coffee Talks. So basically informal talks on topics on the boundary of geography and statistics, and generally about integrating statistical information with geospatial information and seeing what sort of wonderful things we can produce. My name is Stephen Vale from United Nations Economic Commission for Europe in Geneva, and I'll be facilitating this session. First, I have to give the apologies of the chair of Global Forum for Geography and Statistics, the organisation behind these coffee talks, Vilni. Vilni is at the moment, I think, in Vienna Airport and having some problems getting Wi-Fi with sufficient bandwidth to join us, but hopefully he'll be with us before too long. So today's talk is really looking at developments with global grids for statistical data. We've had coffee talks touching on this subject over the past couple of years, but it's also an area where there's some interesting new developments going, and we can see a clear progression in what's happening. So hopefully we get some good ideas and maybe some inspiration about how global grid systems can be useful in our work. As usual with the coffee talks, we have the format of 2 presentations and then an open discussion. The first presentation will be a sort of a double-hander with Kevin Saar, who will start from Southern Oregon University, and he'll be followed for the second part of this presentation by Richard Barnes. And then after that, the next presentation will be by Alexander Kmoch from University of Tartu, talking to us about SageGrid, the proposed project around that theme. So I think we have a nice progression of different ideas about how to use global grids. Anyway, that's enough of me talking. I'll hand over to Kevin, and Kevin, you have about 15 minutes on basically getting started with DG Grid, everything we need to know about hexagonal DGGs. So over to you, Kevin.
Oh, thank you, Stephen. Are you guys seeing my presentation okay? Is it up on? All right, excellent.
Yeah, okay. We see it. Yeah.
All right, so my intention here is just to give a quick introduction to DG Grid and how to get started, how to start running DG Grid programs and producing discrete global grids. All right, so just some basic terms real quick. I'm sure if you're here watching this, you already know what a discrete global grid is, but it's just a grid of regular polygons that partitions the surface of the Earth. And if we take a series of resolutions of a discrete global grid, we get a discrete global grid system. And often we talk about the difference in these resolutions by referring to the aperture of the discrete global grid system. And the aperture is just the ratio of cell areas between resolutions. So an aperture 3 grid, as we increase the precision of the resolution, finer resolutions, we go 1/3 the area of the previous resolution. So just some basic terms. So what is DG Grid? Well, it's an open source command line C++ program for generating and manipulating discrete global grid systems. And I think it's safe to say that it's the most used software for dealing with equal area hexagonal discrete global grids. And that's primarily because it's been around since 2003. The first public release was in 2003. And DG Grid was originally developed with funds from the U.S. Environmental Protection Agency, and since then it's been developed from various government agencies, private companies, and a lot of volunteer effort. In addition to the command line program DG Grid, there are several wrappers for DG Grid out there that allow you to access DG Grid from particular environments. In particular, I want to point to the R environment with DG Grid by Richard Barnes, who's going to talk about that next. And there's various Python wrappers, including DG Grid 4Pi by Alexander Kmoch, who's also going to be speaking today, though not on that topic. So DG Grid supports a fairly wide variety of discrete global grid systems. They're all icosahedral discrete global grid systems. That is, they're based on the icosahedron. And it produces grids that are cells that are triangles, quadrilaterals, or hexagons. And DG Grid supports 2 projections. The ICEA projection, the icosahedral Snyder equal area projection, which is of course equal area, and also a fuller projection, fuller Dymaxion projection, which does a compromise between area and shape distortion. So most people use DigiGrid for the ICEA projection because it allows easy statistical analysis because all the cells have equal area. They're all the same size. DigiGrid supports, so I want to focus in specifically on hex discrete global grids, which is primarily what people use DigiGrid for. DigiGrid produces grids with apertures 3, 4, or 7, or any mixed sequence of those apertures. And you can specify custom DGG settings, or you can choose from built-in presets. So I'm going to just focus here on a couple of presets, in particular the ICEA 3H grid and the Planet Risk grid. So the ICEA 3H is an aperture 3 ICEA discrete global grid system, so it's an equal area discrete global grid system. It's the closest thing I think that exists to a sort of standard hexagonal discrete global grid system, again, because it goes back so far. It goes back almost 20 years. Planet Risk grid is also an ICEA discrete global grid. It's got a mixed aperture sequence that's primarily aperture 7. The advantage to the Planet Risk system is that it was designed to have a particular resolution that has as close to 1 kilometer squared area per cell as you can get with these mixed aperture hex discrete global grids. So the ICEA 3H, being an aperture 3 system, gives you more resolutions to choose from, sort of a finer stepping between the resolutions, and the Planet Risk gives you a 1 kilometer cell if that is of use to you. The other useful thing for these two grid systems is that they both have references. People have already used them, so if you're not really familiar with the options in terms of discrete global grids, you're safe choosing one of these two. So I'm giving you here the references for those two grid systems. If you want to see grid characteristics like the resolution sizes, Appendix D of the DigiGrid manual, which comes with the DigiGrid distribution, has all of that resolution information as tables for those grids and several others. All right, so that's a little background. Let's talk now about how to get started using DigiGrid. So the first thing you need to do is get DigiGrid. DigiGrid is available on GitHub at the link I've given you here. If you're familiar with GitHub, of course, you can just clone that repository. Otherwise, here I've just given you a little graphic so you see the code button there, press on it, and you can download a zip of all of the source code. Once you've got the source code, there's an install.md file in the source code, main source code directory, and that gives you instructions for building DigiGrid using CMake. Thanks to Richard Barnes, incidentally. And that's the way I recommend that you build DigiGrid. That's very easy, very straightforward. There's an alternative build system there that I used for my playing around, but you should ignore that and use the CMake build system. The only external dependency of DigiGrid, it's an optional dependency, and that's the GDAL, Geospatial Processing Library. If it is installed, CMake will find it and link it with DigiGrid. It's not required, but if you don't have GDAL linked with DigiGrid, then you're going to lose out on a lot of file types, for instance, input and output file types. And also there's more advanced features in DigiGrid that depend on the GDAL library. So I recommend, if you can, to install DigiGrid with GDAL. Now, when you run the CMake instructions and build the actual program, that's going to create a command line executable named DigiGrid. And the way DigiGrid operates is, the idea is you're going to run DigiGrid, and it's essentially going to execute a single discrete global grid operation. So it's a one-pass program. You run it at the command line, and it produces some sort of result. So it's designed to be part of a larger command line workflow. So for instance, you could generate a grid in DigiGrid and then import it into a standard GIS and manipulate it there, populate it, and so forth. If you want to interact with a DigiGrid and do a series of operations, with a DGGS and do a series of operations, then at least for now, you're going to have to use one of the wrappers like DigiGrid R or DigiGrid 4Pi that we mentioned earlier. So what are the basic operations that DigiGrid does? Well, there's 5 basic operations. First, and primarily, it generates a discrete global grid, so all or part of one resolution of a discrete global grid system. There's also an operation that performs address conversion. So for instance, if I've got point locations in latitude and longitude, I can use this operation to get the corresponding DGG cell indexes. You can also do point value binning. So if I've got a set of lat long coordinates with associated data values. This operation will bin those values into DGG cells by taking the average of all the values that fall into each cell. There's presence-absence binning. In this case, you give it a bunch of files, each file representing some class, and then it checks to see which of those classes are present in each cell and outputs a vector of zeros and ones that corresponds to whether or not that class is present in that cell. And finally, there's an operation that will output a table of characteristics for a particular discrete global grid system. And there's lots of sort of minor idiosyncratic sort of operations that DigiGrid does off of these that I'm not really going to be able to describe. These are all basically people that paid me to do a particular thing that never got integrated with the whole system. But for that, you really need to read the manual. We're just going to do the basic operation here. Okay, a little bit on the output produced by DigiGrid. So what does it produce for cell IDs? Well, it has a number of different address forms you can specify for the output cell identifiers, but by default, it simply numbers the cells at a particular discrete global grid resolution from 1 to the number of cells at that resolution. So each cell has a unique identifier, and that identifier is constant for that particular resolution of that discrete global grid system. And this is the address type seqnum, which is the default. So if you don't do anything, that's what you'll get as your cell identifiers. Now, various operations are going to generate a set of cells. You can choose what kinds of things you want output about the cells. So you can have the boundaries of the cell's output, the center points of the cells. You can also output the neighbors of each cell. So what are the adjacent sequence numbers to a particular cell? And you can also output the spatial parents or children, that is the cells that overlap that cell at a coarser or finer resolution. By default, nothing, or I don't even know what the default is, to be honest, but by default, essentially all of these are turned off. So you want to pick which ones you want output. All right, so how does DigiGrid actually work? Well, as I said, each run of DigiGrid performs a single operation. The parameters for what that operation is going to do are contained in what I call a meta file. And this is simply a text file that specifies how DigiGrid is going to operate on that particular run. So usually at a minimum, you're going to specify what discrete global grid you're going to use, so some discrete global grid system and a particular resolution, and the operation you're going to perform. And most operations have lots of other parameters that you can set or change and so on. All parameters have default values, and that's what you'll get if you don't specify something. And meta files can also contain comments. These are simple lines beginning with a pound sign. So each line of the meta file that isn't a comment consists of a parameter name and a value for that parameter. So for example, let's say I want to use an ICEA 3H discrete global grid system, and I want to use resolution 5 of that discrete global grid system. These are the two lines that you'd put in your parameter file. The DGGS type specifies the DGGS, and then the DGGS resolution specifier specifies the particular resolution of that discrete global grid that you want to operate on. For detailed information on the parameters, and I recommend in general, anything you want to do in DigiGrid, read the chapter in the manual for that desired operation. That's where all the little secret, strange things that you might possibly do are sort of hidden. The chapters are very short, they're very concise. It's not particularly fun reading, but I think I've captured there all the information you need for each of the operations. So I highly recommend you read the 1 or 2 page section for whatever operation you're trying to perform. There's also a table of all the parameters with all their possible values and information about them in Appendix A of the DigiGrid manual. And finally, in the source code distribution, there's a directory, examples, that contains a whole bunch of example meta files with input and output files, and actually the expected output from those DigiGrid runs. So you can look at those for ideas on how you might work with your own operations. All right, so with that background, let's real quickly now, let's see some examples of DigiGrid in action at the command line. Let me see if I can switch my... are you seeing my command line here?
Yeah, looks good.
Excellent. Okay. All right. So here I am. I'm just in a directory. Oh, wait. Let me first show you. All right. So I've downloaded DigiGrid from GitHub, and you'll see here the install.ms MD file that I spoke about that contains the instructions for making with CMake. And then there's also a copy of the DigiGrid manual. And there's that examples directory that I mentioned. All right, so I've done the CMake compile of DigiGrid, and I've moved the DigiGrid executable into a location in my path so that I can actually use it. And then I've got some sample meta files here. So first off, here's a simple meta file that outputs a table of grid characteristics for the ICEA 3H. So I've specified the DigiGrid operation as output stats. The DGGS type is ICEA 3H, and I want the maximum resolution in my table to be 15. I can set it to whatever I want. And then all the other parameters have default values. So now to use that meta file, I simply say DigiGrid and the name of the meta file. And we see DigiGrid outputs the current value of all parameters that are used by this particular operation. So if you kind of want to see what parameters you could change, these are all here, and I'm just scrolling through them quickly. Obviously, you can look through that yourself. And then here is the actual output, a table of grid information for the ICEA 3H up to resolution 15. So cell areas, note, I should have mentioned, and you're probably all aware, Hex DGGS people, that there are always 12 pentagons in any resolution of a Hex discrete global grid system because you can't tile the sphere with just hexagons. So these first 12 are actually pentagons, and then as we go down, we get about a 1/3 size decrease in the area of the cells. And here we've got the number of cells. This last field is what's called the characteristic length scale. That's the radius of a circle that's the same area as the cell. And that's just meant as a sort of an indication of sort of the compactness of the cell. Okay, so I can get grid statistics for whatever grid I might want to work with. So let's actually do something now. Let's do some grid generation. So first, I've got a meta file here that generates a 1 resolution planet risk grid resolution 5 for the entire Earth. So the DigiGrid operation is generate grid. The DGGS type is planet risk grid. The specification is resolution 5. I want to do the entire Earth. So the clipping subset is the whole Earth. I'm not going to clip it at all. And then here I'm going to specify the output files. And I want to get cell output, the boundaries of the cells, and I will get point output, the center points of the cells. And here I'm using built-in KML type. This isn't the GDAL KML, which is also available. This is just one that I wrote before we had GDAL integrated with DigiGrid. So I specified the output type for the cells and the output file name. And the same thing with the point output. All right, let's run this meta file. And again, we see all of the parameters here that are used in a grid generation operation. And we've generated 4,322 cells. So we want to take a quick look at that. I'm just going to open it in Google Earth. Oh, which you're not going to be able to see, are you? Well, all right, well, let me go ahead and finish these, and then I'll show you Google Earth. I'll switch over to it. All right, so let's go ahead and generate just a portion of a grid. So here's another meta file, similar to the last one. I'm going to use the generate grid operation. This time I'm going to use the ICEA 3H resolution 15, so about 3.5 kilometers squared per cell. And I want to use the GDAL file format for the input. So my clip subset type is going to be GDAL. And then I'm going to specify one or more files that contain polygons that I want to clip the grid to. So all cells that overlap any of the polygons indicated in these input files will be included. So in this case, I've got a GeoJSON file that gives the boundary for Benton County, Oregon, where Oregon State University is located. And then my output is going to be similar to the last time. Both I'm going to output KML files for the cells and the points. All right, let's run DigiGrid with that one. And it gives me some feedback, and it generated 566 cells. I'll go ahead and open. I'll just open the cells file. Let me see if I can switch over to all right, are you seeing my Google Earth Pro window?
Yeah.
Yes. Okay, so that's here you see the outline of Benton County with resolution 15. I see a 3H cells on it. You can also see here we've got resolution 5 planet risk grid cells. And the various points, the center points for those. If we zoom in, you'll see the cell identifier numbers. Again, these are just cell sequence numbers. And so, of course, DigiGrid does have some primitive binning capabilities, but I thought it would make more sense, since they are so primitive, for you to see those sorts of operations in a more sophisticated environment like DigiGrid R. So that's all I've got. If you've got any questions, next up would be Richard Barnes to talk about DigiGrid R.
Great, thanks, Kevin. And just while we're swapping the screens over here, so Richard will, as Kevin said, show how this can be then implemented through R. And as he mentioned earlier, there are R and Python interfaces, so it starts to make it easier for those of us who are not so expert in dealing with some of these more command line based approaches. So Richard, I see your screen. You have the floor.
Okay, and can you hear me?
Yeah, loud and clear.
Okay, very good. So I'm Richard Barnes from Lawrence Berkeley National Lab, and I'll be talking about DigiGrid R, which wraps DigiGrid inside of an R environment. And the benefit of this is that then we can use the full capabilities of R in order to do the loading of our data, subsequent analysis of our data, and saving it. And it also means that we can use DigiGrid R in any environment that allows us to interface with R, which happens to include Python. So the web address is rbarnes DigiGrid-R at GitHub. And if you wanted to install this, you would just do this DevTools install GitHub rbarnes DigiGrid-R line right here. Just briefly, let's take a walk through what's going on here. So in the background of this image, we have the foveal retina. This is the center part of your eye. And when evolution set out to design a high resolution sampling system for the world, you tiled your eye with hexagons. Doing this with the Earth is kind of a good idea if you want to do the same kind of sampling yourself. Your brain was also designed to do mapping based on hexagons of different nestings. So some ideas that are already in widespread use. And what we really want to get to is a place where we have equally sized bins, because that allows us to do spatial statistics in a way that's not biased by any kind of fuzziness about the size of the bins we're putting our data into. And ideally, we don't want to worry too much about map projections. Now, the problem with getting spatial statistics wrong is that then what you end up studying is not your data. What you end up studying is the space that you project your data into. And so the purpose of DigiGrid-R, the purpose of DigiGrid, is to avoid that kind of problem. And it's not as easy as you might think. If you have an equal angle grid, you end up with itty-bitty cells sitting up at the top here. If you go for constant area grids, then you end up having cells that don't nest together nicely. So you might think, well, maybe there are other projections that escape this, but it turns out that almost any projection you choose ends up having quite a bit of distortion. But just looking through these here, these projections onto unfolded polyhedrons of the Earth have pretty low distortion. And to get one of those projections, you make 4 choices. You choose a polyhedron to unfold the Earth onto, you orient that polyhedron, you partition it, and then you transform data from a spherical environment onto one of the faces. And you can remember these choices with the Popped Gourmet Popcorn logo. So just to be clear, we're going to take the Earth and we're going to project it onto one of these Euclidean solids. And the icosahedron is the one that I'll be talking about today, but there are other choices available out there. And once you've projected the Earth onto that polyhedron, you have to choose, well, where is my North Pole? And that has this effect of deciding where the corners of the triangles constituting that solid end up. And for most purposes, this isn't too important, but the projections that are chosen by default in dgGridR and dgGrid are going to put those points in places where they're generally unobtrusive. And this is nice because when these faces come together, that's the only place where we can't get a hexagon on the surface, because as you can see, at least for the icosahedron, there are 5 different triangles meeting at one point. So no hexagon is possible there. And then you have to choose how you're going to partition those faces. You can choose triangles, diamonds, hexagons. These are just all subdivisions of each other. And then how will those nest? So this is the aperture that Kevin mentioned earlier. And once I've got a face, how do I map data which lives on a kind of curved sphere over that face onto the face? We're going to be using the Snyder equal area projection, and so that tends to be a fairly good choice, but there are some others you could make that have different statistical properties. So this is the grid system we end up with as being kind of a solid balance of the properties that you want. And dgGridR is in widespread use for a variety of statistical purposes, soil information, measuring the length of global fire seasons, determining where protests happen and why, studying the flight patterns of birds across the Earth, anything where your data is spanning the globe so that the difference in cell size becomes significant for any system other than using hexagons. Phylogenetics, even landslide mapping. So again, this is where you get the software, and in a moment, I'm going to do a little live demo here. Can you still see the screen?
Yeah, looks fine.
And the text is legibly large?
Good enough for me.
Okay. So here we are. We've got some R code up here. Down at the bottom, we've got a terminal, but you could use Jupyter Notebooks for this if that was your preference. And we'll just load up these libraries. And the first thing we're going to do is we're going to construct a discrete global grid system. And we've got a lot of different options for doing that. The projection I mentioned earlier, the aperture, whether we want diamonds, hexagons, triangles. And then we've got the spacing option, which right now in metric is telling us that we want 1,000 kilometers between adjacent faces or between the centers of adjacent cells. And since we can't get that exactly, we tell the system, well, it's okay if you round down. And the system takes all this information and says, well, the best we can do, given that, is this resolution 3 discrete global grid system. And actually, the intercell spacing that's possible is 880 meters. But if we were to look at the properties of this system, what we would find, and I'll make this window bigger, Kevin showed you this chart earlier, is that there are a variety for different resolutions, and we can fine tune if this level 3 wasn't sufficient for us, we could specify manually that we want the level 2 or the level 4 grids adjacent to it. So having chosen a grid system, we load some data. dgGridR comes with this kind of test data set called dgQuakes, And this is just a list of where earthquakes took place on Earth over the course of 2015. So this is the time the quake took place, the magnitude, and the latitude and longitude. Now the latitude and longitude themselves are not good for doing spatial statistics. So what we want to do is to bin the quakes into some kind of hexagon so that we can say something about regions of the Earth. And to do that, we pass the latitude and longitudes to dgridr, and we get back the sequence number. So when I have a global grid system, and that's tiling the Earth with hexagons, we can label those hexagons from 0 to some very large number, and that uniquely identifies that cell on the Earth for that particular resolution of grid. And so if I pass that to ggrid, and then we look at our transformed data frame, what we find now is that each quake is associated with a hexagon that it occurred in. And because there are a lot of earthquakes, some hexagons contain many such earthquakes. So let's do some stats here. We can group by the cell number, and then we can ask, well, how many earthquakes occurred in that cell? And running that command gives us a new data frame that has that information. So hexagon 6, wherever that was on Earth, had 330 some earthquakes. And now we can ask, well, what are the boundaries of the cells in which those earthquakes appeared? And this says cell number 1 is bounded by this set of lines. So knowing how many earthquakes occurred in which cell and where the cells are, we can combine that information. And now we have a data frame that has earthquakes and cells in the same set of information. And we'll just take a log count of the earthquakes, we'll cut it off, and then that's going to give us something that's a little easier to plot, load in a map of all the countries on the Earth. Some grid cells cross the international date line, so we can wrap those around. And then let's grab the center of the cells. To do that, we pass the cell number back to dgridr, and it's going to give us the center point of that cell. And then we've got our standard ggplot commands here. So we're going to print out the countries of the Earth with black borders. We're going to print out the cells, coloring them by the number of earthquakes that took place inside of them. And we'll print the center points as well. And when we do that, we get this map. And so this is, although these cells in the map appear to be of all kinds of different sizes, that's just an artifact of the fact that we have to project this into a 2D space to visualize it. But if we had a sphere, all of these hexagons would be very closely the same size, and they're colored by the number of earthquakes occurring within them. So mission accomplished, we're able to take continuous data scattered across the Earth, put it in equally sized bins, and then talk about those bins. But wait, there's more. We could construct a global grid system, and we could pass it a shapefile and ask, give me the grid that covers that shapefile. And having done that, we can plot that. And South Africa, it turns out, has little islands down here in the bottom right. So the set of grid cells that cover all of South Africa, or the bounding box thereof, is shown on the screen. And this allows me to then do things like presence-absence binning. So having all of the cells available, I can ask which cells were filled and which cells were not when I threw my data onto this projection. And then Vilni, who I think has arrived now, asked me, here's 300 megabytes of housing data for Norway. How long would it take to process that? I'm not going to run it now, but I can tell you that loading that data takes about 28 seconds. Downsampling the data takes about 1 second. Since every algorithm here, it has a time complexity of order n, if we just multiply it by 5, that gives us the final times. So the buildings data set is projected into this UTM zone 33. We can reproject that data, and that's going to bring it into WGS 84. That'd take about 10 seconds on the full data set. And we can tack the XY coordinates of the buildings back onto that same data frame. And so now we have a set of data like this. We have the building serial numbers, the type of the building, where the building was located. Let's make a grid with 20 kilometers between each cell. Oh, and that might be the end of my live demo because I've made some kind of typing mistake somewhere. Yep, not seeing it offhandedly. In any case, each of these commands takes only a few seconds to run, and the longest running commands are going to be for this 3 million point data set, converting those into sequence numbers. That takes about 45 seconds. But after you've done that, everything else just goes along swimmingly, and you can plot Norway's buildings that way. So does anyone have any questions?
I'm not seeing any burning questions now, but I would encourage people to think of your questions, and after the next presentation, then we'll have an open discussion where you can ask away. So I propose, we have something coming in on the chat now from Peter at ISPRA. I don't know if you saw that one, Richard. What happens to points which lie on cell boundaries or even junctions?
Yeah, so I think the short answer to that is I'm not sure. But to get a point that lies exactly on a boundary is going to be kind of a mathematical challenge. It's just going to end up arbitrarily in one of these cells. So if your data is sensitive to points lying on the boundaries, I think that that's probably going to be problematic for analysis generally. Because either you have too few data points, and so you're losing the statistical nature of the data, and maybe you should work with the data as individual points, or maybe you're choosing cells that are so fine that the amount of space, as it were, that's on the boundaries comes to dominate your data set rather than the area of the cell. But for any cell of a non-trivial size, the amount of points that fit within the cell greatly exceeds the amount of points that fit on its boundary. And so in a statistical sense, these should all wash out. I hope that answered your question.
Great.
Yeah, sorry. At a technical level, DigiGrid is going to do something, and that's going to result in the points uniquely ending up in one cell. We just, I can't tell you which one. And if it matters, then that's a different problem.
Oh, it looks from the chat like Peter's happy with your answer, so thanks, Richard. Let's go to the next presentation now, where Alexander Kmoch will perhaps bring this in a little bit more into the European context and tell us about ideas for a project at the European level that will build on these things that you've seen in the last two presentations. So Alexander, over to you.
Yeah, so I guess you can see the presentation here. So hi everyone, I'm Alexander Kmoch, Alex, if you will. I'm a geospatial researcher at the University of Tartu in Estonia. And earlier this year, we have developed a grant proposal for a Horizons Europe call. And I'll talk a little bit about that. So like all European grant proposals, you have to have a cool acronym. So we came up with SAGEGRID, Spatial Analysis Area Statistics and Aggregations as a Service with Discrete Global Grid Systems. And that was for the call World Leading Data and Computing Technologies earlier this year. So we built a consortium of about 16 partners, and we tried to reach out to as many grid enthusiasts as we potentially could. We were a little bit under time pressure, so we didn't probably reach everybody, but feel free to reach out. So the thing is, the proposal wasn't successful. We just recently got the information that it won't be funded. We are very keen on resubmitting to the next suitable call and improving the proposal. So that's why we sort of share this information here right now, more as a sort of transparent gesture, in desire of potential collaboration, because typically those proposals are quite competitive and nobody likes to share their ideas, of course. But we going maybe to go a different way, because the whole thing is only going to be sort of successful if as many people know about it as possible. So a short sort of executive summary right now. It aimed at the European data strategy. So the European Commission is developing a new data strategy, and there's something called Envision Data Spaces, where it's all about sort of a thriving data market and value-added data products. So we point in there to develop sort of a spatial trade paradigm based on discrete global grid systems. How is that intended to work? Well, as Kevin and Richard really nicely explained, everything is really nicely going down to quite uniquely identifiable cells that are nicely distributed across the globe. So basically a data trade paradigm based on this ID-based encoding of data that allows for a very targeted, very seamless data selection. And shall make it easier for actors in the data market to sell and buy and thus use small data packages, in a DGS format, as compared right now as it is. You have to download large amounts of data. If it's a remote sensing data, you have to currently still download the whole scene, which is several gigabytes. So you have to convert and reproject in order to extract pixels for your potentially much smaller area of interest. And then similarly, combining data, let's say from different national and international agencies. Again, you run into the situation of having also to reproject. Spatial data services like OGC standard-based services are already really good at that. But another challenge is indeed recombination. So DGGS software is becoming increasingly available, even though some things are already long time available and have matured quite nicely. And DGGS is ideal for data aggregation and data fusion, especially also from different data sources, and particularly if we talk about different spatial resolution and formats. And one particular curious effect is, as Richard also showed, in the end you end up with a really nice table, and each row in the table is representative for one cell on the area. So extraction and tabular alignment of observed data is really nice and useful for machine learning processes. Things like random forest, which is inherently not spatial, but in this way you can really nicely align and aggregate and combine data from different sources. One of the main things that we really hoped, and again hope to achieve if that project would be going forward, would be to mature the software ecosystem around DGGS and API standardization. So for that, we are also involved with the Open Geospatial Consortium, DGGS working groups. And another thing regarding open scientific software and open software as such in general, to involve with the Pangeo community. So a short background. So that was one of the catches sort of in the first place. So DGGS as a common geography will ensure that all statistical data is consistently geospatially enabled and that all users can discover, access, integrate, analyze, and visualize statistical information seamlessly for geographies of interest. So as sort of a bit reiterating here, as we increasingly need to combine tabular and spatial data, spatial units, over which we aggregate, like such as raster pixels of remote sensing or various vector geometries, points, line, polygons, And then we have, let's say, arbitrary units like cadastral or administrative units, or agricultural fields that are varying in size, shape, and again, spatial coordinate reference system. That is quite challenging to get a really good, evenly, statistical aggregation and summaries over those areas. And once we go global anyway, it becomes really, really complicated. From, let's say, inconvenient that you just, more processing, you need more reprojecting, you run into issues of spatial alignment. Even if you would use same resolution, same projection, raster data or gridded data, the grids, if they are not aligned, you still have an offset, so you still run into a spatial alignment issue. Or, as also Richard nicely demonstrated, outside wrong results, pixels or grid cells in global raster data sets don't have comparable sizes. The more you run towards the poles, the more you run into distortions, or depending on the cartographic projection. So, and then coming down here to our host spatial statistics divisions across national and international agencies often use their own square-based reference grids. So in Europe, where we have the European Union, but we also have the individual states that have their own statistical agencies, their own statistical grids to aggregate, for example, population statistics, and then have to do the reporting to the European Central Agency, where the European grid is not the same grid like used on a national level, so you run even into regridding issues. So these things we really wanted to address with that proposal. And for that, we of course chose discrete global grids. That would be, the ideal technology and methodology to do that. From the upper part, different population grids, for example, from national agencies, they don't align well if you want to combine that, let's say, on a European continental level, and then aggregating them over a globally applicable, standardized, uniquely identifiable equal area grid, like we can see here, courtesy of one of our partners, that in different cells you can have, aggregate values, all sorts of values, and combining cells even from different origins, as long as you have the cell IDs, always that these data are easily combinable. So, and the Pangeo community, for those of you who don't know, so Pangeo is a, let's say, loose, in Europe, still quite loose, community of scientific software developers and users, mostly scientific, but they're really representing the open source packages that are used in scientific computing, which is like the Jupyter notebooks, the Xarray gridding, and these type of scientific Python libraries. And we thought it'd be absolutely fantastic if we would engage with this community. Sort of, you have this Earth observation, data science, and the scientific computing environment where the people really make sure that the software stays compatible, is composable, and if we would get that ecosystem to mature to work with nicely hexagonal equal area grids, that'd be a major step forward in acceptance and sort of making this concept of working with spatial statistical data even more easy and useful across domains. Another thing is also, for example, this is just an example here. So this is the Copernicus land cover in DGG Grid summarized for Estonia in a Purchase 7 hexagon equal area grid with resolution 8. So, and that's based on remote sensing raster data. But of course, as we've seen before, also binning point data and then being able to combine these type of things for large scale computing and spatial analysis and statistics, it would be a fantastic move forward. So one thing that I really wanted to bring up here is you might have run across the web, all sorts of people now, startups and also established GIS companies using hexagons. And everybody says, hey, we use hexagons. Hexagons are great. But one thing that is really important for you that I thought is an interesting background just to sort of keep in the back of your head is that most of the hexagons you see in, let's say, modern startups are based on H3. So Uber H3 is also a hexagonal hierarchical geospatial indexing system. And the hexagons are, it's quite similar to ggGrid in the sense that you have hexagons at different resolutions. So Uber H3 uses an aperture 7, where 7 children comprise sort of the same area at the parent cell. So that is fixed, and also the rotation of the icosahedron is also fixed. So, but what you probably didn't know about H3 is that H3 is not equal area. So one of the things here is just repeating, each cell has a unique ID, which is great. So to uniquely identify a location on Earth. The software ecosystem for H3 is quite nice because it has libraries in almost all popular programming languages. So this is a big thing, probably what I think has been helping really to the uptake of H3. You can do spatial analysis by functions with like k-ring and distances. And as Richard also showed, group by via cell ID, so that's all really good. Pentagons were already shown, that's fine. Aperture 7, as Kevin likes to say, aperture 7 is 2 large steps. Kevin likes aperture 3 and 4. Aperture 7, but aperture 7, as you can see, you can more, for some people, this type of nesting and hierarchy seems to be intuitive. And then so aperture 7, you have uniquely identifiable 7 children of one parent. But as you can see, it's not actually fully enclosing, just so that on the size. But the most important thing that you need to know about H3 is that the cell size is very much more than you potentially expected as compared to the ICEA ggGrid grids. So ggGrid can produce close to almost equal area cells, but H3 does not do that. So, and other useful GGS software, of course, ggGrid, then RHELPix and Google S2 and OpenEGA are also software libraries that can build global grids of some sort. And the grids look, for example, like this. So H3 on the left side is an aperture 7, but it doesn't use the Snyder equal area, but it uses the gnomonic projection, and that's why the cells are not equal area. ggGrid can actually generate a variety of equal area grids. And then OpenEGA, Triangular, RHELPix, they are also equal area grids. Curious RHELPix from Landcare Research in New Zealand uses a variety of different cells. So that's also a bit sort of non-intuitive probably for many, but the grid is quite equal area. And Google S2 is also a spatial indexing system that is based on the cube sphere. So you also get lots of distortions, but again, you can index cells quite nicely with Google S2. So one of the things that, as I said, uptake regarding software. So for H3 and for Google S2, there's the cell indices, the IDs that you generate can be immediately understood and be translated and transported between platforms and still be understood. So if you load a data set that only has cell IDs and a value, softwares will be able to easily convert it in and out. For example, in this Kepler GL web spatial visualization. So I think that is a big plus for these type of libraries, something that I would really like to see for other ggGS software as well. Coming back to the cell distortions, because that's really important. as you can see in the middle here, Uber H3, and at the bottom, Google S2 have large areal sort of distortions. So cells in different places in the Earth can vary plus minus 30, 40, up to 30, 50%, whereas DG Grid is basically same areas across the globe. Our heel picks similar as well. And how does it look like if you would use H3? So as you can see, the pattern is of course based on the base solid, which is the icosahedron, and you see the distortion, sort of overly large cells in comparison to the mean are red, and two small areas in comparison are blue, and those are the corners, sort of the base solid, and then the central areas. That is based on the internal projection that H3 uses. So here, that's just really important. Even though H3 is also easy to use, you really have to take into account that you have these different areas. And then in comparison, Google S2 here on the bottom right, again, also has huge distortion. So it's not meant as sort of a binning and statistical tool, but it is at least good for generally indexing data to find where data points are. And then DG Grid and our heel picks on the left side are really smooth, fantastic. So regarding the consortium of our grant, so why I gave this background is really that some of the due diligence, just knowing what's out there, and of course in the grant, in the proposal, we would really want to mature the ecosystem about equal area grids. Currently, we are a consortium of 16 partners across Europe, from across sectors, academia, governmental organizations, and industry. So we have research organizations, others than university, but we also have universities. We have startups, tech incubators, and administrative divisions. And we have divided that, basically the activities in the grant, the way we built the grant, into parts that are more into maturing the ecosystem, building the software ecosystem for easier uptake, test driving use cases across domains. That, for example, the statistical agencies really, would be like our testers, for example, and some universities that would look into actual sort of like landscape biodiversity. They would use that, as a means of spatial aggregation and statistics, but not actually the development of the software. And then we have capacity building. Here we are also engaging, as I said, with OGC and the Pangeo community and the tech incubators, where we would sort of plan hackathons and all sorts of events to train, provide documentation, provide uptake, so sort of like this open source software ecosystem. The use cases include, of course, spatial statistics and reporting, but we also have ocean and land sciences teams that would see if, because their current use is either classic raster grids, square-based raster grids, or in the ocean and atmospheric sense, they use a lot of unstructured grids that are very similar to triangle-based grid systems. So we have a couple of partners in that space, which whom we would consider, test driving that, so that we would get in the end with a like the one grid system, that can cover all the things basically, and so that's sort of part of the scientific bit to really see if there's really the potential of a grant unification. And of course, in the Earth remote sensing Earth observation space, satellite data is still, for let's say normal people, difficult to just get some pixels for their smaller areas of interest. Data fusion is a big topic because you get remote sensing data from a bunch of different satellites in different resolutions, with different characteristics. Making that accessible is always a huge effort. Another important topic, of course, risk management and analysis, because here again, we look at spatial aggregates and spatial analysis sort of on similar areas and statistics, and spatial planning and municipal administration support. These are sort of the use cases that we envisioned. And we have managed to link a large part, let's say, of the global DGGS knowledge globally and in Europe to the consortium. Because the point really is the more people know and the more we share, the more has the whole thing the potential to be the change that we want. So, and if you would be interested in that type of work, feel free to reach out. We are, as I said, we have to find another good call where we can apply with a grant like that. And of course, we would have to develop the grant according to the call, or we have to be quite focused. But in general, that's sort of the idea, and we'd be very happy to build the network. Yeah, so reach out to us, Alexander Kmoch at University of Tartu, Landscape Geoinformatics Lab. Find me on Twitter as well. Okay, thank you very much. That was me. So stop sharing.
Great,
Where's the
thanks,
button?
Alex. So we had a question in the chat about presentations being available. As I mentioned at the start, we're recording the session, and the recording will be posted on the GFGS wiki. So I've just put the link to the page in the chat, which is where the recording will appear as soon as I get a chance to download it and put it onto the wiki. I also put in the chat the contacts for the Global Forum for Geography and Statistics. So Vilni, who is the chair, and myself as the sort of secretariat, really, I suppose, informally. So if you're interested in the work generally of the Global Forum for Geography and Statistics, or if you want to propose a topic for a future coffee talk, then please get in touch with us. And not least, I also added the emails of the three presenters because I think they would all be very happy to hear from you if you want to follow up on some of the things they've been talking about. But of course, we also have the chance for a few questions now. So I would like to open the floor. We can do this in various ways. You can type in chat, but it's probably easiest if you just either put your hand up or just unmute and ask a question. So does anybody want to get started with the questions? So Hugo in Canada is posting something in the chat. Any of the presenters using hexagons, so wondering what are the limitations of the system. For example, if you want to use smaller hexagons, like around 100 square meters or even smaller, is it possible for the DGGs to manage this over large areas? So yes, very, very fine resolution. How does it cope? Who wants to answer on that one?
The answer to that, as far as I'm aware, is that the projections, getting the cell numbers to work just fine, even down to 100-meter resolution. However, if you're trying to generate a global grid at that resolution, you're going to run into a serious issue where that's going to take a lot of space. So feel free to do statistics at that level, but if you're doing global statistics, plotting that is not going to be something you want to try.
Yeah, I can concur. Kevin, yeah. It's totally possible. We have done, let's say, national level things with a resolution where we have a rough diameter of around 9 meters, so which is like 75 square meters or something. So if you pre-generate the grid, of course, it will use quite a lot of space, but it's possible.
Okay, so I see the hand up from Luis de Souza. Luis, do you want to take the floor to ask your question?
Yeah, thank you, Stephen. First of all, good afternoon, everyone. This was really an interesting hour. It had been quite a while since I had such an interesting hour. Anyway, I have, if I recall correctly, a few years ago, DG Grid was implementing the IZ projection only in the spherical form. And my question is whether this is correct or if the ellipsoidal form of the projection has been implemented already.
I'll answer that one. It is just a spherical form. Some users, so for instance, the ESA for the, I can't remember the name of the soil moisture database in the ESA, they simply take the spherical form and interpret it as ellipsoidal coordinates. So of course it's no longer exactly equal area, but the variation is fairly slight over the surface of the Earth. But it is indeed just a spherical projection at this point. So that's.
Okay, thanks. Other questions, comments? Alexander?
If I have the chance now to talk to Kevin and Richard here, that I would it's a very technical question. The identifiers, right? So the identifiers, the segnoms, converting between those and the cell and cell geometry. Does that work the same across the different DGGS types? I ran into something that didn't work as well with ICR 7H, which might be working with ICR 3H because the type is not pure but sequenced. It's a very technical question. Do you know what I'm asking?
No, I don't. And Alexander, you can reach out to me anytime. I mean,
okay.
anyone here can reach out to me anytime. So I'm not sure what you're referring to. So you'd have to be more, maybe give me an example meta file that's producing the error.
Yeah, sure. I'll be happy to send something.
Okay.
And yeah, sorry, I'll wait, of course.
No, if you have another question, please go ahead.
Yeah, the GDAL version, is there a, I don't know, like restriction upper or lower version, which is compatible, something that maybe to consider if you compile it yourself? Does it have to be like GDAL 3.4 or 3. Something like that?
That's a very good question, but I don't think it really matters because the use of GDAL is really just the file types, and now I'm using it for some of the sort of geometry operators, but they're all things that have been around for a long time in GDAL. So I don't think you'll encounter any difficulties. Certainly if you do, let me know, but it's not specific to a particular version of GDAL.
That's cool.
And in wrapping DGGrid and DGGridR, I haven't noticed any compatibility issues with GDAL. Occasionally, you get issues where the Proj library used by GDAL is unable to find its list of projections, and usually some digging on the internet explains how to point it in the right direction.
Okay, final chance for any questions to the presenters. Not seeing anything in the chat or any hands up. In the chat, Peter. Good occasion to also point at OGC's DGGS domain working group, which is always happy to get new members and facilitate new applications.
Yeah, I can quickly say 2-3 words. So the OGC DGS domain working group is to a large extent also interested in the API web service development around making DGGS encoded data or DGGS index data available. So, I mean, to a large extent, we're not developing DGGS systems like Kevin does, not as such. So we would rather currently, as far as I see, I'm also a member of that working group that where to large extent rather make it more accessible, building on existing software. So we'd be, of course, happy to have more members who want to try those things.
Great, thanks. Yes, Peter's follow-up. Yes, it's all about usage. Yes. Okay. I don't see anything more at the moment. These sessions we always advertise as approximately 1 hour. We started a few minutes late and we've gone a little bit over an hour, but I think we're still in the approximate time schedule. So it just remains for me to say thank you very much to the presenters, particularly for the very early starts over on the far side of the United States. Thank you very much for joining us at this crazy hour in the morning. So with that, I would like to close this coffee talk. As I mentioned earlier, we'll post the recording on the wiki and the addresses in the chat, so grab that while you've got chance, and hopefully we'll see you all again at a similar talk sometime soon. Thank you very much.
Thank you very much, Stephen. Thanks, Kevin, Richard. Great talk.
Thank you.
Thank you.